All right, so now we're going to talk about angles and radian measure. These are uh, slides from textbook where this was in section 4.1. These are the same slides that I use in my on-campus class and everything. So you will see that a bunch of these are worked out already. So we're going to kind of talk through them and see what we need to do and everything. So that way we kind of have a good idea of everything that's going on. So some terminology that we need to make sure that we understand whenever we start talking about angles and radian measures and everything is what are the different sides and everything. So in these cases right here, we're going to have, for this first one on the left side, we're going to talk about where our angle alpha is going to be in standard position. And when we mean standard position, what that means is that our vertex is at the origin 0, 0, and that its starting side or initial side is along the positive x-axis. So that's what we need when it's in standard position. So then that means that our angle is going to be this entire angle here. And then the resulting spot is technically a point, but we're going to draw this as a line here. And that's going to be our terminal side. So anytime that we say it's in standard position or in general, if we're just talking about an angle, that's going to be where we're focusing everything at. If we're going to be in any other orientation, it's going to be clearly defined. So like in this second one here, it says that our angle theta is in standard position. Okay. That means that we started along the positive x-axis. But in this case, we're told that our angle theta is negative. So since our angle theta is negative, what that really means or tells us is that instead of going counterclockwise, we're going to go clockwise here. Then we still have our terminal side that's down here. So we got to pay attention to key words inside of the problems because they're going to be very beneficial in telling us, are we going to be going in standard position with our angle being positive, or are we going to be in standard position with our angle going negative and everything? So we just have to keep those two kind of in mind so that way we kind of know what's going on. So some other types of terminology that we need to think about whenever we're doing things is, what is a degree? What is meant when we say 90 degrees, 45 degrees, stuff like that? So a degree is a unit of measurement used with any angle. So 1 degree is equal to 1 over 360 of the complete rotation. So what that really means is that inside of a complete circle, that there are 360 degrees. So for positive angles, we're going to go counterclockwise. For negative angles, we're going to go clockwise. So we just have to make sure we understand which way we're going, depending on if we have a positive or a negative angle. So with that, we've got different types of angles that have different special classifications and everything. So for an acute angle down here, so an acute angle is any angle where our angle theta is going to be greater than 0 degrees or less than 90 degrees. So if we think back to our XY axis, an acute angle is anything that's in here, anything between the positive X and the positive Y. A right angle is also 1/4 the rotation of a circle, which is equivalent to basically saying we're on the X and Y axis there, the positive Y axis and the positive X axis. Versus say an obtuse angle is any angle that ends over here in the second quadrant, because theta has to be greater than 90 degrees but less than 180 degrees. The last standard type of angle that we've considered is what we call as a straight angle. So a straight angle is anything that, if we think about XY coordinate, it's anything that is directly on, begins and ends over here. So in other words, we begin here, we end here. This would be our straight angle, which has a measurement of 180 degrees. So there's really only two types. We have a right angle and a straight angle that really have their own special designation for a specific number. So we're given three of these right here. We want to know whether or not they are acute, obtuse, or straight. So one easy way is to draw them out. So 140 degrees. So we start here, 140 degrees, puts us about right there. So we know that it's greater than 90. So in other words, it had to land over here to be acute. Obtuse is over here. And straight is on the line. So therefore, 140 degrees by where it lands is our obtuse angle. Don't let weirdness confuse you now, because it's E degrees. Well, remember, E is 2.718 approximately. So approximately 2.718 degrees means that my angle would be right here. So therefore, it gives us the acute angle. The last one is 180 degrees. So if we draw our line, this would be our 180 degrees. So therefore, that gives us a straight angle because it ends on the x-axis. So we've got to be able to make sure that we understand how to classify angles, so that way we can easily know, kind of get an idea of where they land, where they start, where they stop, stuff like that. So at any point, we can always transform or be given angles in different measurements. We have two types of measurements that we consider. The first type of measurement is a degree that we were just talking about. The other type is a radian measure. So 1 radian is the measure of the central angle of a circle that intercepts an arc equal in length to the radius of the circle. So let's think about that in a different way, because I know that can be confusing. So consider an arc of length S on a circle of radius R. The measure of the central angle theta that intercepts the arc is given by theta equals S divided by R radians. And when we write these, we normally don't want to, we'll normally leave it in terms of pi, something times pi, unless it tells us otherwise. So inside of this, we could have a circle centered at 0, 0. And then we could see how this could become this circle or this circle, where this one might have, say, radius equal to 1. This one might have a radius equal to 2. And we could keep going and have a radius equal to 3. Yes, I know these aren't quite looking like circles, but we will assume that they are circles. So we can just see different things that can be done, and we can sweep this entire thing in terms of starting and stopping these at each points. So we're going to disregard that this is here right now, just so that we know. So we're told, find the radian measure of the central angle of a circle of radius 11 that intercepts an arc length of 12 yards. So we know that our definition stated that theta equals S over R. So we need to be able to figure out which one is which. So in this case, S is equal to 12, R is 11. So this is 12 over 11 radians as our answer. So always make sure we can identify what we have versus what we're needing. So we can always convert from degrees to radians or radians to degrees, given these two simple formulas here. So depending on which way we're going will depend on which formula we're going to use. And that in turn will give us our process. So to convert degrees to radians, we're going to multiply our degrees by pi radians divided by 180. And we're going to simplify this into a fraction. Unless otherwise specified, we want to leave everything as a fraction here instead of a decimal, because a decimal is not fully accurate. Unless it were to come out to even like 0.5 or something like that. So to convert radians to degrees, we want to multiply our radians by 180 degrees divided by pi radians. And if we do that, that will give us a answer that is in radian measure. So let's look to see how we can do that. So I'm going to go ahead and cross out these answers here, so that way we can work it out on our own. So 135 degrees to radians. So we're going to have 135 times pi over 180. And we know that we could divide each of these by 45. So that's 4, and that's 3. So we get 3 pi over 4. We could do the same thing with 210 degrees. This is 210 times pi over 180. We could divide everything by 30 in this case. So we get 7 and 6. So we get 7 pi over 6. Now, keep in mind, this one said the 2 decimal places versus the first one said in terms of pi. So we would just want to pull up our calculator at this point and calculate it out. So when we do 7 pi divided by 6, if we round this to 2 decimal places, we get 3.67 as our answer here. So now we're going to go the other way. So we're told to convert this to degrees. So given 8 pi over 5, we're going to multiply by 180 over pi. So our pi's will cancel out. So we'll have what? 1440 over 5, which is equal to, because this should divide evenly, looks like 288 degrees. So on this next one, negative pi over 11 times 180 over pi. So we get negative 180 over 11. This one says round it to 2 decimal places. So we get negative 16.36. And a lot of times we don't like working in terms of negative. So what we found here is that negative 16.36 is right here. That will be the same thing as if we were to take this and come this way and land on that same terminal side. So in order to do that, if we add 360 degrees to get to that, this is the same thing as 343.64. So just kind of pay attention and everything that they are the same. Normally we like to write stuff with positive exponents. So in terms of trig, we like to use a lot of fractions. And what I mean by that is if we start with a circle, then technically we have our X and Y axis. So we have only one piece. This is just one piece separated by our axis. But if we were to draw lines through it, we would create 4 pieces. Then I could then take and draw another one over here and get 12 pieces, depending on if you count your axes as pieces or not, and everything. So in other words, all we're doing is we are partitioning a circle into different pieces. So this one gives me 4. Then we have 8. And we have 16. So we can partition this into as many different slices and types of slices that we want. We do have some standard ones. So one thing that can come in common is we can either work in radians or we can work in degrees. So some people like to more work in degrees than radians. It all just depends on how you're looking at it. So in terms of 11 pi over 6, where are we going to be at with this one? So 11 pi over 6, if we converted it, would be 330 degrees. I like degrees a little bit more, depending on what I'm doing, but I try to work back in terms of the problem. So 330 degrees is going to put me here, which would put me in quadrant 4. For negative 3 pi over 4, so negative 3 pi over 4 is going to put me here, which would be in quadrant 3. We're just looking at where is the final terminal side going to be at, not certain things, but just what the terminal side is. That determines our quadrants. So we're told, without converting, draw the angle in standard position and state the quadrant. Okay, so I've already stated the quadrant over here and drawn it, but let's just think about this. One entire revolution is 2 pi. So in terms of 6, this is 2 pi over 1, which would be the same as 12 pi over 6. So if I were to subtract this, 21 pi over 6 minus, so 21 pi over 6 minus 12 pi over 6, I get 9 pi over 6, which is now less than 2 pi because 12 pi over 6 is there. So that means that I'm somewhere inside here. But 3 pi or 9 pi over 6 is going to reduce to 3 pi over 2 if we were to divide each of them by 3. So therefore, my new value is actually this one. Technically, it would be 1 full revolution and then pick up from there. So then it looks like this right here, because the 1 full revolution is this 12 pi over 6 that we subtracted out. So now that we've worked with radians, now we can do the same thing with degrees. Degrees is a lot easier to me because we can easily see it. So 150 degrees gives me this angle right here. So therefore, the quadrant is quadrant 2. Negative 90 degrees puts me here. So therefore, technically it is not in a quadrant because it's actually on a pole. So we might just say that it's on a pole instead of actually stating that it's in a quadrant here. So two angles are said to be coterminal if they have the same terminal side. So in other words, we could see different values that still get us to the exact same ending spot and everything. And so that's why we have a special name for them called coterminal, meaning that they end on the same spot, but they may not have the same characteristics going to that spot. So 30 degrees is this line right here. 390 degrees is this line right here. And negative 330 degrees gives me here. So notice that in all cases, they all end on that same line. So therefore, all three of these values are coterminal because they begin at the same spot and they all end at the same spot. So we're told find a positive angle less than 360 degrees that is coterminal with the given angle. So in other words, we want to find the first positive angle where this one is coterminal with. So in order to do that, we need to add multiples of 360 together until we make it to the first positive number. So we would have 360, 720, 1,080. So this is my first number that is positive and above negative 1,000 there. So if I add 1,080, I get 80 degrees. Adding 1,080 is the same thing as saying 360 times 3, because here's 1, here's 2, and here's 3. So what if we had find a positive angle less than 2 pi that is coterminal with the given angle? So notice that we're in terms of fifths. So 10 pi over 5 is going to be a 1 revolution. 20 pi over 5 would be a second one. So if I were to minus 20 pi over 5, I would get pi over 5. So therefore, by taking 21 pi over 5 minus 10 pi over 5 times 2, we get 21 pi over 5 minus 20 pi over 5, which is just pi over 5 here. So that would be my positive angle that is less than 2 pi and it's coterminal. So we've already seen a similar equation definition here a few minutes ago. So when we see this, let the length of a circular arc, so let r be the radius of a circle and theta the non-negative radian measure of a central angle of the circle. The length of the arc intercepted by the central angle is given by s equals r theta. So we already found a way to find theta. Now we can find a way to find the length of our circular arc. So just s equals r theta. So some things to keep in mind here, let me jump back up here, is that r is the radius and theta is the non-negative radian measure. Has to be in radians. So therefore, find the length of the arc S on a circle of radius r intercepted by a central angle theta. Express our arc length in terms of pi and then round to 2 decimal places. So if my radius is 6 feet and my central angle theta is 345 degrees. So the first thing I need to do is I need to get my theta in terms of radians. So I need to convert 345 degrees to radians. So 345 is equal to 23 pi over 12 because we're going to multiply 345 by pi divided by 180 and simplify. Once we do that, we can plug directly into our formula of s equals r times theta. So we get 6 times 23 pi over 12, which is the same thing as 23 pi over 2, which is approximately 36.13. Because it told us to round to 2 decimal places. So we need to always think about what we're doing here, but don't get so caught up in it that we just get totally confused on the basics that we're trying to do. So the minute hand of a clock moves from 12 to 7 o'clock. Through how many degrees does it move and how many radians? So let's think about this picture now. So the minute hand of a clock moves from 12 o'clock to 7 o'clock. How many degrees did it move and then how many radians? Well, on a clock face here, if we were to draw everything out, we kind of align this, we kind of look like this. So if we were to draw lines here, 1, 2, 3, then 4, 5, 7, 8, 10, 11. So how many spots do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 evenly spaced spots. So 360 degrees divided by 12 spots gives me 30 degrees. So each number on here represents, when we go from 12 to 1, that's 30 degrees. 1 to 2, that's another 30 degrees. 2 to 3, that's another 30 degrees. So if we went from 12 to 7, we would have 1, 2, 3, 4, 5, 6, 7. So 7 times 30 degrees is 210 degrees. So now we need to take this 210 degrees and we need to convert it to radians. So we take our 210 times pi over 180. They're both divisible by 30. So make that a 7, make that a 6. So we get 7 pi over 6 in terms of radians. So once we have one of them, we just do the easy conversion. So the last thing that we want to talk about is degrees, minutes, seconds. So 1 degree of a complete rotation is 103, 1 divided by 360th of a complete rotation. 1 minute is equal to 1/60th of a degree. And 1 second is 1/60th of a minute, which is going to be 1 over 3600th of a degree. So anytime that we're looking at this, we need to be able to see how we can go from one to the other very easily. So we're told use a calculator to convert the angle to decimals, to a decimal in degrees, round to 4 decimal places. So the first thing, we're going to start from the right-hand side and work our way in. So first thing is, we're going to take this 49 minutes, or 49 seconds, sorry, 49 seconds, and we're going to divide it by 60. So 49 divided by 60 gives me the 0.81667. Then we're going to take that 25.81667 minutes, and we're going to divide it by 60. So we get 0.4302778. It told us to round our final answer to 4 decimal places. So therefore we have that 37 degrees, 25 minutes, and 49 seconds is equal to 37.4303 by rounding the answer that's on line C right there. So what if we want to do it the other way? We're given the degrees and we want to convert the angle to degrees, minutes, seconds. Round to the nearest second. So what we want to do, we want to work the other way. So in the previous one, we were dividing by 60. And this one, we want to multiply by 60. So first we're going to subtract the whole number. So 32.23 minus 32 is equal to 0.23. Then I'm going to take that 0.23, I'm going to multiply it by 60. I'm then going to subtract the 13. I'm going to take that 0.8, I'm going to multiply by 60. So every whole number we subtracted goes in order of degrees, minutes, and then the last number is our seconds. So we subtracted 32, so it's 32 degrees. We subtracted 13, so that's going to be 13 minutes. And then the last number that we had left over was 48. So therefore we have 48 seconds. So 32 degrees, 13 minutes, and 48 seconds would be the full expanded degrees, minutes, seconds form that we're looking for. So hopefully that gives you a good talk about angles and measures, and therefore we're ready for our next section.